Hello, everyone. Welcome to another episode of Clay Loves Logic, where on this channel I solve logic-based puzzles, Sudokus, anything of the sort I find interesting. Today we're going to be solving the puzzle In a While, or See You Later in a While by Michael Lefkowitz. As always, I'll put a link to this puzzle in the description so you can play it along if you'd like at home. Let's read the rules. Normal 6x6 rules apply. You have to have the digits 1 to 6 in every box, in every row, and indeed in every column. Killer. Values in a cage sum to the number in the corner. These two sum to 0. These two sum to 0. These two sum to 1. These three sum to 21. Okay. All right. Negators. The value of a digit on an alligator is negated, so it won't count. Crocodoublers. The value of a digit on a crocodile is doubled. They look the same. We have to deduce which is which. See you later, negator. In a while, crocodoubler. That's funny. Okay, well, what's this digit? All right, the triangular number of 6, i.e. 6 plus 5 plus 4 plus 3 plus 2 plus 1 is 21. So 6 and, 21 and 3, you just have to double the 6, right? Because 6 doubled is 12. Add the next two biggest digits, you get 5 and 4. 5 and 4 is 9. That's all this can be. Just going to give us a 1, 2, 3, 4, 5, 6, and a 1, 2, 3. Okay. So now let's look at these, right? These zeros. Well, a zero is going to have to just be a Kropke dot, right? A 1, 2, a 2, 4, or a 3, 6. Because if you double a 1, you get 2. You subtract 2, you get 0. That's sort of that 2 to 1 relation. A 2 to 4 is the same thing. Double the 2, you get 4. Subtract 4, you get 0. A 3, 6, same, right? Double 3, you get 6. Minus 6, you get 0. That means, I think that means that this is always going to be a 3, 6. This one can't be a 3, 6 because there's a 6 here. And there's only 3 possible Kropke dot options, 2 of which share digits, right? 1, 2, 2, 4. So this couldn't be 1, 2, and 2, 4. This is a 3, 6. This is from 1, 2, 4. And then this would be, 5 and something else. 5 and either, 1 or 4. But what's interesting about that is that's going to give us a 4, which is going to give us a 5, because we know there's always a 5 here. And actually, a 4 being in this row is always going to put a 4 here. So that's always going to put a 1 here. This is now a 2, 4. So that's not a 2, and that's not a 1. Which means this is from 1, 3, and 5. And then this is going to be, 1, 2, or 4. It can never be 3, 6 because there's always a 3 or a 6 here. Well, let's look at the 1 cage now. A 1 cage, what's the biggest you could double is a 3. You double a 3, you get 6. You subtract 5, you get 1. The next biggest digit's a 2. If you double 2, you get 4. You subtract 3, you get 1. There's always a 3 here. I'll put a corner pencil mark so we know. Always a 3, no matter what. 3 comes out of there. Okay. Now where do we look? Well, we have a doubler here. We can't double a 3 now because the 3 is always accounted for. You can't. Oh, but we could negate it. Okay, if we negate it, the biggest it could be is a 5. Then this could be a 6. Okay, maybe that's not immediately interesting. Oh, this could never be a 3 because of the 3, 6 here. So in fact, that means this is from 1, 2, and 4. And then this is from 2, 3, and 6. And I want to claim now that we know that this is from 2, 3, and 6, I want to claim that it's never a 2. Because if it's a 2 and you double a 2, you get 4. If you double you add the biggest digit you can, which is a 6, that's 10. These are just, you can see that these are never high enough. This is never a 2. And by the same logic, how could this ever be a 3? You double 3, you get 6. Add 6, you get 12. You know that you need 5 and 4. We can't do it. This is always a 6 and it's doubled. And that should honestly solve this 21 cage because we're going to have to get to a value of 9. We're going to need to get to 9. There's just no way we can't, right? This is 12. We need 9. And we can't double anything. So 4, 3, and 2. There's never a 1 in here. This is a 1. This is a 3. This is a 2. This is a 3. Yeah. And then this is not a 3. This is a 1, 5 pair. Just has to be. So now where do we go from here? Oh, 3. Oh, that gives us a 3. This is a 3. Sorry, this is a 3. This is now not. This could be a 2. This could be a 5. We're not sure yet, but what we know is there's a 3. Where do we go from here? Well, we need a 6 somewhere here by Sudoku. So we can't have a 6 here or here. One of these is a 6. And if this is a 6, it's only a negator. Oh, no. Can't be either. There's no way you make this 1. You double 6, you get 12. You subtract 6, you need a 7. This is never a 6. It's silly. This is a 6. Which means that's not a 6. And 6 is now in a few different spots up here that are interesting. At least this one's interesting. If this is a 6, this has to be a 5, and it's the negator, and that would give us a 1. Possible. Okay, let's turn our attention to the 21 cage and let's start asking some questions about what can be doubled and what can be negated. Is there a world where this is the doubling cell? I'm going to claim not. Because if we double 2, we get 4. And if we subtract 4, we get 0 and they cancel out. And then, 6 plus 5 is only 11. And that's never high enough. This is always going to be the cell we subtract. And how's that going to work math-wise? If we double a 4, let's just think about some math here for a second. We double a 4, and then we have to add 5 and 6. 5 and 6, 11. Double 4 is 8. So we get a value of 19. And then we need to get to a value of 3. So we could add 3 and 1, which would be 4, and subtract 2. That works. No, it doesn't, does it? Let me think through that again. Okay, 5 plus 6 is 11, plus double 4 is 19. 3 plus 1 is 4. That gives us a value of 23. Yeah, minus 2 is fine. Yeah, okay. Well, then let's just do the... Well, then I think that has to be it, right? We can't double a 5, I don't think. If we double 5, we get 10. We add 4 and 6, that's another 10. We're already at 20. We can add 3 and 1 is 24 minus 2. Yeah, no, that doesn't work. This is a 4. This is 5, 6. And then what did we say? This has to be, well, let's take the 4 to there for now. What did this has to be a 2 now? 8 plus 5 and 6 is 19. 3 plus 1 is 23 less 2. Yeah. Neither of these are 2. This isn't a 2. And now what? This could be 2, 1, or 4, 2. Oh, this is a 5. Which means this is no longer a 6. This could only be a 6 if this was a 5. So what do we have left now? Oh, and this is a 6 actually because of the 5. This is a 6, this is a 5. This is now only from 1 or 4, right? Yeah, this is a 6 always. This is a 3, this is a 6. Surprisingly, 1, 2, 4. So this is a 5, this is a 1 because of the 1, 2, 4 triple. 1 means 4 means 1 means 2 means 4 means 2. Okay, now we need 1, 2, we need 3 and 5. This can't be a 5, so this is a 3. This is a 5. This is a 1. This is a 3. This is a 1. This is a 5. This now has to be, well, I guess it just has to be a 2, doesn't it? Because 3, and then you negate 2 gives you a 1. So this is a 4, this is a 2, this is 1, 2, 3, 4, 5, 6, this is 1. Beautiful puzzle. 10 minutes solved. You've solved the puzzle. 10 minutes, 19 seconds. 76 people solved, 10.6 hours. That was a fun puzzle. Michael Lefkowitz. I really enjoyed that. Quick one today. Very fun puzzle. Good intro to some of these concepts and fun math. Right, everyone, thanks for tuning in, and we'll see you on the next one.